Hey, last time we were talking about factorial and what factorial gives us. We found out that it gives us the number of unique arrangements where order matters. And the arrangements are of size n and elements, there are n elements in each arrangement of size n. And so we sort of just took examples of making arrangements and we sort of made sense of what this is in factorial. Now we're going to be talking about combinations, or might have heard this as n choose k. And the difference between a permutation is they're both arrangements. I have A, B, and C. I've got three distinct elements here. A not equal to B, not equal to C. But with a permutation, I have order. It means that there's a sense of position here. I might have A, B, C. I might have another permutation, which is made of the same n elements, but I could just switch the order somewhere. And so ABC and ACB would be considered distinct and unique permutations or distinct and unique arrangements because order matters with a permutation. With a combination, that's not the case. The order doesn't matter, just the size, and size meaning how many elements are in the arrangement. But the way that they're ordered does not matter. So in this case, there would be two permutations, two unique arrangements where order matters. But if we were to look at both of these permutations and say, okay, given these two permutations, how many combinations do you have? You just have one. So ABC is equal to ACB. One combination. What is this n choose k formula showing us up here then? Well, we see another variable here which we haven't looked at yet. That variable is k. So n is still n. It's the number of distinct elements that we have. Set, for instance. And k is a variable that we're going to enter now. K is a limiting variable on the size of each arrangement. Or, we just, within factorial, we're like, well, it's a size of n, and there are n distinct variables. Well, now we're going to kind of take a look, what if we kind of said k was the size of each arrangement? So let's go ahead, and we're going to look at set of n equal to 3, A, B, and C. But we're going to be looking at two different cases. So the first case is we're going to be looking at a specific value in minus k. And we're going to be asking how to describe permutations in k is not equal to n. when k is less than n. And then the second case is we're going to be doing the same thing. We're going to be looking at what happens when n is not equal to k, but we're going to be looking at how to describe nations. When k is not equal to n, k is less than n. We'll be looking at these two cases, case 1 and case 2, and we're interested in case 2 especially because in looking at case 2, we're going to find this and choose k equation right here. So case 2, we're going to be finding this formula and choose k here, which tells us how many unique arrangements there are, where each arrangement you can select from n distinct elements, but there is a size k of the arrangements that they have to be, k positions. And it's combinations, the number of the combinations. That means order doesn't matter. So you will see this in the binomial theorem. Like this is how Pascal's triangle is built. Which is pretty cool, and we'll go into that. But first, let's just start by looking at the permutations. Okay, so let's go ahead and let's make our arrangements, our unique arrangements of permutations. And let's start like we did when we were looking at factorial. K is equal to 3, so we have size 3 for each of these arrangements where order matters. So let's take a look. So our n minus k, in this case, is 3 minus 3, which is equal to 0. So in this case, we have not changed or limited anything. Let's go ahead and fill out these tables. So we know in the first position, I can choose from n different values. I'll choose A, B, and C. Fix A, I'll switch C and B. That's 2 arrangements. That's all I can do here. So now have B in the first position, A and C. Those 2. Now for B, C, A and B, and then I can switch to 2. So these are our unique combinations. Given we have n distinct elements to choose from, and the size of each arrangement, order matters, is 3. So we can see here that we have there's no difference here between what we saw for n factorial. N factorial would describe what we see right here. But what we're going to consider this time, K. So K is, in this case, equal to 3. We have a size 3 for each of these. But K is not a variable that is independent, right? For instance, I can't have like an arrangement of size 4 in this case, right? Because then K would be equal to 4, but n is still equal to 3, so I could be like A, B, C, but there's nothing here. I've already run out of distinct elements, so that's not possible. So K does depend on n for this reason. And so what we can say about K is the size is we know that k has to be less than n. Well, less than or equal to n, right? In this case, it's equal to, which is fine. Um, so what we might want to take a look at next is, okay, what what if k is not equal to? Now, before we move on to that, though, let's talk about combinations. So, given that we've introduced what k is now a variable. You could think of it as the variable that corresponds to the columns here, right? Because if I have 1, 2, 3 columns, and if I had n minus k is equal to 1, then that would be the same as taking away one of these columns. And then the leftover would be 2 columns. These would be my unique arrangements. So let's take a look at combinations. So a combination, like we said, order doesn't matter. So that means that for what we're looking at, ABC is equal to ACB is equal to EAC is equal to ECA, CAB, CBA. So if all of these are equal, how many unique combinations do I have? I just have one. Just one unique combination, right? Technically, there are 6 of these, but that's not 6 unique combinations. These are all the same. So I have 6 identical combinations here. And so if I was to say how many unique combinations do I have here, I just have one. I have one unique combination and 6 identical combinations. And that's kind of why it's useful for the polynomial, for the binomial theorem, because obviously x times y, or let's say x times y times z is equal to x times z times y. And so it's going to recognize that these are identical, and it's just going to say, all right, if you were to add these two together, then you have 2 of this. So that's why n choose k is used for the binomial theorem, because it's saying, hey, these are all the same. I'm going to add them together and then spit out how many you have. That way, you don't have to look at this freaking, x plus y raised to the 50, right? Like, I can just tell you coefficients, which tells you how many identical combinations you have. So pretty useful. Yeah. So and I said we were going to look at case 1 for each of these. So case 1, all I can say right now is that when n minus k is equal to 0, seems like if we wanted to come up with like a formula that describes to us how many permutations you might have, kind of seems like it's the same as in factorial, right? Nothing has really changed when n is equal to k. See. And then as far as case 2, when we're looking at combinations, when we're looking at combinations, what we found was that this sort of collapses down to 1. All these, one unique combination, right? So you could say 6 identical combinations or one unique combination. In this case, yeah, let's just say one unique combination, because that's what this is telling us. Unique combinations, it kind of seems like you have n factorial divided by n factorial, right? Because if the amount of unique combinations here, 1, maybe it's n factorial over n factorial. Or maybe it's n factorial over k factorial. No, not really sure. You could also be n minus k factorial, which in this case, n minus k factorial, 0 factorial, which is equal to 1. So it's not entirely clear to us quite yet. Like, how would we guess what's going on here? So let's take a look at what would happen if we now got rid of an entire row. So say if I get rid of this row right here, what that means is that I now have a size 2. And if I was to describe this row that I'm eliminating here, though, I wouldn't say k equals 2. I would probably say something more like n minus k. If I was to describe this row that I'm eliminating, it's n minus k is equal to 1 now, as n is 3 and k is 2. Right? So let's see what happens there. Go ahead and get rid of it. Okay, so we're gonna look at the permutations first. And notice is that in removing a row, right, or a column by saying k is equal to 2 now, it kind of looks like nothing has changed, right? I mean, we still have like 6 permutations here, right? So kind of, I think instinctually we would probably think, hey, if I'm, removing a column, then there's a chance that I'm reducing the amount of permutations. But in this case, after removing this, it's not really the case. Now, what if I remove an entire row, or 2 rows now? So now k is equal to 1, and n minus k is 3 minus 1, which is equal to 2. So I removed n minus k rows. Let's see what happens. So now you can see that it has affected the amount of permutations, right? Because we no longer have unique permutations. I have A here, and A here. Not unique. I would have to get rid of one of these. Same here. So by removing 2 rows, we actually are going to be halving the amount of permutations. So when you are halving something, I think this is when you begin to think, okay, that means there has to be a factor in the denominator, right? So if we look at the case for permutations, where n minus k is equal to 3 minus 1, which is equal to 2, and we can see that now the amount of permutations is being cut in half. So I think that what that tells us is that there has to be a factor in the denominator, right? Because we had n factorial, but now, because we are actually beginning to lose unique arrangements when we get rid of these columns, we know that something is going to have to be in the denominator. So we could guess maybe k factorial would be a good descriptor here. But then you would have 3 factorial over 1 factorial. And that just doesn't really describe our situation. Then you have 3 times 2 over 1, which is 6. And that doesn't describe what we have in this situation, right? In this case, we have 3 permutations now, and we used to have 6. But that's not really a good descriptor either. So then, if we try different things, maybe we can try maybe we can try n minus k. Because ultimately we are taking away n minus k rows over here. Okay, so n minus k in this case is 2 factorial. Maybe that's a little closer. If 2 factorial is 1 times 2, 2. So then you would have 6. So that, it looks like it's closer. It looks like a pretty good fit then. If we were to just take a wild guess about how to express how the permutations are going to change when I just straight up like shrink the size by 2, then it looks like this is describing permutations pretty good. We'd have to use induction to prove that that's the case. But for now, we're just going to accept that this here describes permutations. And we could test it real quick on another case as well. We could test it just to be thorough. We could go back and we could test it. Give you B, you C, A, you C, give you A, give you B. So now let's go back to 2 and let's see if that describes our situation that we just picked. Let's see if that describes our situation in this case. We see that there are 1, 2, 3, 4, 5, 6. There are still 6 permutations, even though I removed one of those rows. Look, so we have n minus k. N is still 3 factorial. N minus k is 1 factorial. Again, that's just 1, so 6. So it looks like this is going to work. So we'll just accept for now that this is describing the amount of permutations, given that we allow the size of the arrangements to vary. So then, now let's take a look at the combinations. So for the combinations, let's go ahead and take a look at the current case that we have, which is k is equal to 2 and is equal to 3. So even though I removed the row, that doesn't affect the combinations at all. It doesn't affect permutations or combinations, it looks like. Because nothing here is, even though we removed a row, the fact that we have 3 distinct elements to choose from, and now we're just being constricted to a size of 2, it doesn't matter. Because I can always just have another arrangement that has the other distinct element in it. So no effect in this case. So not terribly interesting, but we might guess that just like for permutations, it gets smaller. The amount of permutations, unique permutations, gets smaller as we remove the rows. We're going to see the same thing with combinations. We might guess that would be the case, right? So then let's take a look. So for combinations, for the previous case that we looked at, the case where n is equal to 3 and k is equal to 3, we found for that one that we had one combination. Okay, so one combination, and we took kind of a little bit of a stab at it, and we said, okay, so maybe then it's n factorial over k factorial, because in that case you have 3 factorial over 3 factorial, so then get 1. So we could try and see what happens in this case. So in this case, the number of combinations does not change. So let's take a look at a different case. Well, actually, let's go through with this case real quick. N equals 3, k is equal to 2. That's what we're looking at here. So we already can see that the sort of formula that we took a stab at to guess the number of combinations already doesn't fit, right? Because k is now equal to 2 factorial, and so you would expect to see 6 over 2, which would be 3 unique combinations. but here we still see 6. So we already know that, yeah, maybe this isn't really what we're looking for. So why don't we go with, the one that was working for permutations? Let's just take a look, see what happens. So in this case, you would have 3 factorial over 1 factorial, and obviously that does work actually in this case. So, well, actually, I'm sorry. I'm sorry, it does not work in this case. And the reason for that is you have AB here and BA here. So these two are not unique. So if we're looking at combinations, then this doesn't work. We have to take away this one, because A times B is equal to B times A. That one is not unique, so I'm going to take it out. This is not unique, as B times C is equal to C times B, and for the same reason, we have to take out this C times A. So we actually have 3 combinations in this case. So you have 3 combinations in this case. So then for the previous one that we had, it would actually work, it looks like. So you would have 3 factorial over 2 factorial, which is 6 over 2, which is 3. So maybe it does work. We'll see. So now we have to try out the last case, where we have, see what happens when we have n equals 3 distinct elements and we choose arrangements of size 1. Let's see how many combinations that we have. Let's go back and let's put our list our permutations again. ABC, BAC, BA, BC, CA, CB. Okay, so we have our 6 permutations here. And so now we're going to go ahead and take away another column. That means our size of our unique arrangements is now, so then our n minus k is equal to 2. And in this case, we already said that for permutations, we have repeats, but it's the same for combinations here. Have here, repeat here, repeat here. So we have 3 unique combinations here. Okay, so let's plug that in and see if we get a 3. I have 3 factorial here, and k is 1 factorial, 6. That does not describe how many combinations I have. So then that's where we need to rethink our formula. So obviously we need a larger factor, the denominator. And I think let's just go ahead and try that n minus k factor, since we know n minus k is a part of the mechanism of part of the math of what is allowing us to remove these columns. So let's try that, because I know I need something else in the denominator. K is not going to cut it. Three factorial over k is 1 factorial, or n minus k, which is 2 factorial. So then I know that's going to be 6 over 2, which is 3. So it looks like then we have found the formula for the number of unique combinations or unique arrangements where order matters, given that the size of the arrangements is allowed to fluctuate. And the same goes for permutations. This one is not. This one looks this looks very similar to this one, but that's the important thing to realize is there's a real difference. There's the reason why this is not in the binomial theorem, and this one is. And so yeah, let's just go ahead and this is your n choose k for combinations. And so we've shown how you get this. So let's go ahead and just show the connection here real quick. I imagine quite a few of you already know about this, but in case you don't, you've all seen Pascal's triangle before. And Pascal's triangle is it's literally built from this n choose k combination. So for instance, 0 choose 0, 1 choose 0, choose 1, 2 choose 0, 1 choose 2, 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. And yeah, let's just go ahead and we can prove that real quick. So you know that oops. 3, 1, 2, 3. Yeah, that's correct. Okay. So you know that this is supposed to be 3, right? Let's just try that real quick. You have 3 choose 1 is equal to n factorial, which is 3 factorial, or k factorial, which is 1 factorial, n minus 1, which is 2. 6 over 2, which is equal to 3. So n choose factorial describes every position in Pascal's triangle. And yeah, it's how you would calculate like a really ridiculous coefficient if you needed to do that for some reason. And let's see, is there anything else? Maybe we might want, let's see, maybe we'll take just a couple seconds to explain like what is this? What is 0 choose 0? Like that sounds kind of ridiculous, right? Or 1 choose 0? Like all of these, right? Like in what situation are you doing this? I think this probably makes more sense, right? Because like say you have n equals 1 and k equals 1, that's pretty straightforward, right? Say you have an element A. How many unique combinations can you make from A? You can make 1. That's A. That's why 1 choose 1 is equal to 1. And all of these, 2 choose 2, like it's the same thing, right? You have A, B. I can pick. So for combinations, if it was a permutation, then I would have 2 unique permutations, A, B, and B, A. But since n choose k is measuring combinations, I just have 1. Because AB is equal to B times A. So 2 over 2 is equal to 1. 3 over 3. 3 over 3 is equal to 1. Yeah. So then, maybe real quick, let's just talk about 0 choose 0. So there is a little bit of like a mathematical convention where like doesn't really, I'm not sure how much sense it makes in like a physical situation. But there's something called like the empty set, and you might see it like this. And there are brackets to show that there is no element in this set, basically. Nothing in here. That's what the empty set is. And there's one of these in any given set, because there's always the potential for a set to have nothing in it. So that's kind of where this is coming from. This ing 0, choose 0. So say if I have 0 elements, then I just have like an emptiness. It's like an empty bag, kind of. And it's like, how many unique combinations of nothing can I make from nothing? Guessed it, it's nothing. But that's still 1. So, it's kind of weird, but it's like you can make one combination, even though there's nothing in it, and you have nothing to choose from. But that 0 choose 0 is 1. And so that explains this, and it also explains all of these. Because, I mean, even if you have, some stuff to choose from, you have n equals 2, have a and b, how many unique combinations can you make from a and b where you're not allowed to choose anything? Well, you can make exactly 1. That combination is empty set. Choose to have nothing. But there's only 1 of those. So 1 unique combination. So that's kind of a weird thing, but just in case you're like looking at this and you're like, that doesn't even make sense. That's what's going on with that. So I hope that was helpful. And if you are interested in learning more about combinations, maybe if you're interested in learning about the binomial theorem, how that all plugs in, like how this connects to maybe linear algebra or probability, then just let me know in the comments below. Thank you so much.